Hi. I will start in maybe 30 seconds. So when do you want to? Okay, so it's just we should tell the students when to. Normally we have the cameras maybe off, so I don't know. So when you want to film, maybe you can just make sure we can tell them to switch on the cameras for a while. Otherwise it can, when we are done. So, you know, it's tempting to watch from bed at home, you know, so. Okay. Okay, very good, thank you. Okay, so welcome everybody. Glad to see you with cameras on. It's nice for a change. So today we're going to have the last lecture, and I'm going to try to present 3 topics today. So I'm going to first finish the automorphisms of the unit disk from last time. So we were going to characterize the automorphisms. We're going to give an explicit description of these. The second topic is that I will go back to the bonus problem of the first homework, which is about finding a local inverse to holomorphic functions. And I will show a technique, a general technique called Lagrange inversion, which you might not have seen before in your standard complex analysis course. And the third thing, the last thing that I will want to do is to talk about the gamma and the zeta functions. And I'll finish off by see what we can say, now that we've gone through this course, about the Riemann hypothesis, right? So this will be the goal of today. We have some 10 minutes plus extra. Hopefully this will give us the room needed to go through all of these topics today. So let me first recall. So we are interested in the group here. So D is the open unit disk, and we're interested in the group of the automorphisms from D to D. And we recall that an automorphism meant that you were bi-holomorphic, so which meant that the map F is holomorphic. It has an inverse, and the inverse is holomorphic. But this was actually the same as saying that F is holomorphic and bijective. So this means that F was holomorphic and bijective. Okay, and then we had the following. So we want to prove the following theorem. So we showed last time that any map of a certain form was an automorphism. And today we are going to prove the converse to this result, which is the following, that all automorphisms of the open unit disk are of the following form. They are of the form phi A of z, or f of z, so phi A of z, we call it, which is written like this. So for some real number theta and some complex number A of absolute value less than 1, so inside the unit disk. So any automorphism is of this form, for some real number theta and for some complex number A inside the unit disk. So last time, if you remember, we showed one direction. So we'll prove this theorem now. So this is an explicit description of the automorphisms, which is something very useful, right? So first of all, we already know from last time that any such phi a of z is an automorphism. So for any theta here between 0 and 2 pi, if you want, and any complex number a inside the unit disk. So now we want to prove the converse. So for the converse, we have to suppose that we have an arbitrary automorphism, and then we have to show that it is of this form that I wrote over here on this board. So suppose that F is an automorphism of the unit disk. So then in particular, so it's holomorphic and it's bijective. So from this being bijective, we know that it's in particular surjective. So we can find an A in the disk. Were there any questions? No? Okay, so we can find an A in the disk which maps to 0. Okay? So this is, of course, easy. So you have some bijection here from a disk. So you can find some A that maps to 0. This is always possible. Okay. And then what do we do with this? So then we get this composition of maps, so which maps 0 from the disk. So it maps 0 to A. And then if we apply this again, so if we apply phi A, so we see that phi A of 0 is equal, so note that phi A of 0 is equal to A, right? So we can verify this. But if we take this equal to 0, so we can take a phi A such that which maps here. So actually, so this phi A here will be when E of I theta is equal to 0. So this is A minus Z over 1 minus A bar Z. So this one will map 0 to A because the absolute value, because then this denominator vanishes. So you have this phi A here, and then F maps A to 0. So we can look at the composition of these maps going from D into D. So what we obtain, we obtain this composed map, which we call G, which is F composed with phi A, which we just looked at, such that, so it's a map from the disk into the disk, and G of 0 equals 0. And now if you remember from the last course, this is the hypothesis of a certain result. So which one would that be?
Schwarz lemma.
Exactly. So now we can apply the Schwarz lemma. Okay, so also, by the way, note that why is G an automorphism? So the composition of an automorphism is an automorphism because, the most abstract way of saying it is that this holds because the automorphism is a group under composition of functions. So this composition is still an automorphism, and this holds. So then we can apply the Schwarz lemma, as you said. So by the Schwarz lemma applied to G, what can we conclude? Well, the Schwarz lemma, it said that the absolute value of G of Z would be less than the absolute value, less than or equal to the absolute value of z. It also said that the absolute value of g prime 0 is less than or equal to 1. So you remember there were two possible conclusions from the Schwarz lemma, and this was one of them. This is the one that we will use, okay? So I can write also the other one, but it will not be used right now in the proof. So we had this. On the other hand, we know that G inverse is also in the automorphism group, and G inverse of 0 is 0 as well. So this means that Schwarz lemma again applies also, so it applies not only to G, but it applies actually also to G inverse. And using this, then we see that it's applied to G inverse. So what can we then conclude? We see that absolute value of G inverse prime of 0 is less than or equal to 1. But on the other hand, this thing here, what does it equal? Well, it equals 1 over, if you remember the formula for the derivative of the inverse, it's just equal to this, which, so absolute value, which is equal to 1 over g prime of 0. Okay, so in other words, what we get is that g prime of 0 is not only less than or equal to 1 from the first blackboard here, from here, but we also get that g prime of 0 is larger than or equal to 1. And the conclusion would then be that the absolute value is exactly equal to 1. And this is when we remember the last part of the Schwarz lemma, which would then say that if we have equality in any of these conditions over here, then in fact we have a very special conclusion. So again, by Schwarz lemma, we have that. So maybe someone wants to help me out, by the way. What should I write over here? See the conclusion for G.
G is just rotation.
G is just a rotation, exactly. So what you mean to say then is that G of Z is of the form lambda times Z, where lambda is a complex number with absolute value of lambda is equal to 1. So it means that it's just a rotation. Exactly. So we have this conclusion that G of Z is equal to lambda Z, where lambda is a complex number of absolute value 1. And now we just remember how we defined G over here. So it was the composite of the function f, which was our abstract automorphism from the beginning, and this special automorphism phi a, which was of this form over here. Okay, and the conclusion then would be the following. So, okay, so this means that, first of all, it means that G of Z, this lambda, I can of course write it of the form E of I theta for some theta between 0 and 2 pi. And second of all, this gives then that, what's this? This means that phi, so this is G. Of phi a of z is equal to e to the I theta phi a of z. So I put, in the argument, I put phi a of z, which is equal to this. On the other hand, we remember now, so recall that we saw last time that phi a was actually its own inverse. Phi a was equal to phi a inverse. This we used to prove the lemma. So if you don't remember this, you can go back to the last lecture, to the notes. And using this, we see that, okay, so we have f composed with phi a, composed again with phi a, and evaluated in z. So this thing here is just f of z. So the conclusion is that f of z is equal to e to the phi I theta times phi a of z, where a is this, so it's a complex number in the unit disk, but we can actually say even more, having gone through the proof. A must actually be the complex number which maps to 0, so such that f of a is equal to 0. So, okay, so it is of this form, and this finishes the proof. So any questions about this? Okay, so if not, then let me make some remark. So the remark is that we can deduce similar results. So now we know exactly how to characterize the automorphisms of the unit disk. So the unit disk is a very nice domain in the complex plane, so it seems like this is a very special result. But the remark is that actually it can say something about a very large variety of open, simply connected domains in the complex plane. So we can deduce similar results for the automorphism group of, let's say, omega, also for other domains, omega, which, okay, they have to at least be open and simply connected, have no holes, morally speaking. And I will give an example of this, what I mean. So what I mean, so the example I will give is that we can see that, in fact, the automorphism group of H, where H, so it's isomorphic to the automorphism group of D, where I will tell you now what H is. So H is just the open upper half plane. So it's the space of Z whose imaginary part is positive. So it turns out that, so this is H, and it turns out that this is actually, first of all, H is biholomorphic to D, the unit disk. And moreover, not only are they biholomorphic, but the biholomorphic map, realizing this, this identification between the unit disk and the open upper half plane, actually gives an explicit isomorphism between the corresponding automorphism groups as well. So let's see how we can do that. So I will go now to this board. Hope it doesn't ruin the shot. Okay, so you can think, while I erase, about how you can realize explicitly an automorphism between H and D. Okay, so of course you use, so what do you use actually? Maybe somebody has an idea. You don't have to tell me explicitly, just say the strategy that you would use. Like, what kind of map would realize this isomorphism?
I think Mobius transformation.
A Mobius transformation, yeah. I don't hear you very well, but I heard you well enough to hear you say Mobius transformation, so very good. So we use a Mobius transformation. And then, of course, I could ask you which one, which would be an exercise that you could do, but maybe not in your heads, just in 5 seconds here. So explicitly, we get, so let me write it down. So explicitly, we would get f going from H to D would be given by the following Mobius transformation. So remember that these are all invariant up to constants, multiplication by constants. So you can, for example, write it like this. Or I could write it 1 minus iz, maybe. And then I have an explicit inverse to this. And how do I find the inverse? So this is a nice little repetition of what we did with the Mobius transforms. So first of all, you can note that this corresponds then to the matrix given by 1, minus I, and 1. And then to find the inverse of this Möbius transform, we had to find the inverse of a matrix. And then you have this formula for inverting 2 by 2 matrices. So this one has taking the inverse and not caring about the scaling of the determinant. We would switch places of these and switch the sign here. So we would get 1, 1, I. And then I can go back and I can tell you exactly what would be the inverse here. So it would be the map that sends W to W plus, it's the other way around. So I guess it's A plus, no, it's AZ plus B, or it's A plus BZ? No, it's AZ plus B. Okay, so it was correct, yes, whatever. Okay, so it was 1, it's minus 1. Okay, it doesn't matter. So now, okay, let's see, I don't remember the convention that I had there. But let's anyway, you know how you identify it with matrices. And then I hope that this is correct, that it's IW plus 1 that you get here. Okay, and here we should note that f of I is equal to 0 and g of 0 is equal to I. So why I'm saying this is just to say that when we find the inverse, we could find it up to scaling. Okay, but we have here used a sort of compatible scaling, which says that, okay, I is sent to 0, and 0 is sent back to I through this inverse that we find. Okay, and now the exercise, okay, up to doing this correctly with the identification with the matrices, the projective general linear group, if you remember. What we would get then is the following, which I will leave for you to do at home, is that this f from H to D, so it's a biholomorphism. Check this. Okay, so check. This is what I just tried to explain, but with inverse G. And moreover, we have a map which is induced from the automorphism group of D into the automorphism group of H, which is given by sort of conjugation. So if we take an automorphism phi, which is a map from D to D, then we want to send this one to D composed with phi composed with F, where, of course, morally speaking, I mean, what we're thinking here is, so this is F inverse composed with phi composed with F. So this is some sort of conjugation. And this one gives an explicit isomorphism of groups. This is the claim. So gamma is a group isomorphism. And then as a sort of bonus, you can try to answer the following question. So how can you describe, so using this isomorphism, of course, given an element in D, we know that they are all of this form that we proved earlier, of this form phi A. But then gamma maps this automorphism into something else. And so we can try to identify and describe the image of all these automorphisms and try to describe then exactly what an automorphism of the upper half plane would look like. So how can you describe explicitly elements of the automorphism group of H? So this would be a nice question to try and answer. Then as a sort of homework. Okay, and so the final remark on this part, before I move on to the Lagrange inversion, would be that this kind of identification, so this biholomorphic map from H to D is just one example of a more general statement, which I will not prove or anything, or not even state formally, but it's a more general, it's an especially case of the Riemann mapping theorem. Okay, so biholomorphism from D to H is an illustration of the so-called Riemann mapping theorem, which states the following. It says that every non-empty, open, and simply connected subset of C, with one exception, and the exception is that it cannot be all of the complex plane, so which is not all of C. Okay, so this is important. Which is not all of C, is actually, and this is a very miraculous result, so it's actually biholomorphic to the unit disk. Okay, so it means that if you give me any open, simply connected domain, so I can just draw one, this looks to be an open, simply connected domain, omega inside C, which is not all of C, and it's not empty, so then this one has to be biholomorphic to the unit disk. So a remarkable result. And then, so not in all cases, but in many cases in practice, you can actually realize this biholomorphism with a Möbius transform, or if you can realize it in some other simple way sometimes, like the exponential. And in these cases, you could in fact hope then to be able to describe explicitly also the elements of the automorphism group of omega by using this kind of techniques that we saw on the other board to find an explicit isomorphism also between the automorphism group of D and the automorphism group of omega. Okay. So any questions about this part before I move on to the Lagrange inversion technique? So. Yes, so it's possible. So actually, I think all of them are already there. It's just that they are using two devices, actually. Okay. Yeah, so it's, yeah. One with good camera and one with a big screen, basically. It's okay. Yeah. Yes. Okay. Okay, so if there are no more questions about that, let us now go to the Lagrange inversion theorem. So I hope that this Lagrange inversion is a topic that you might not have seen. At least for me, I definitely did not have this in my first undergrad complex analysis course, which I guess would correspond to what most of you have done before. So let me first remind you then. So recall the homework 1. I asked you, okay, although I stated this, there was some typo. I mean, I should have remembered this local, the word local inverse, of course. So find the local inverse to the function f of z is equal to z to the times e to the minus z at z equals 0. And you could try to describe this local inverse, for example, using its power series expansion. So this was a bonus problem in homework 1. Of course, it was much too difficult back then, and that was done on purpose so that I could now go back in the last lecture and show you how to do this. So how to do this is to use the general technique called Lagrange inversion, which is then the following. So first, okay, so let us recall something about the local behavior of functions. So if we have f, a map from U into C, and Z0 is some point in this open set U, then how could you tell the existence of a local inverse? Do you remember this condition? So a local inverse around f of Z0 exists if and only if some condition. Which one was that?
Derivative is non-zero.
Exactly. So thank you very much. So f prime of Z0 is non-zero, is equivalent to existence. So f has a local inverse around this point that we would call typically W0, which was f of Z0. So we recall this, and then the question would be, how can we find the local inverse? So here we want to find it explicitly. So how can we find it? We know it exists, but now what would the local inverse be? So to see this, let G be the local inverse to f, which is defined then on a neighborhood of f of Z0, this W0. And this neighborhood would then be W0, and the neighborhood would be a small disk of radius delta around W0. Okay, so it's defined on a small disk like this. And then we know, so if you remember by the open mapping theorem, we saw that this inverse was continuous. And even stronger, we were able to show that it was actually analytic, because thanks to the continuity, we could compute the derivative by taking 1 over the derivative of f, right? You remember this? So, in fact, so we saw, you recall, that this inverse G is actually analytic on this disk. Okay, and thanks to it being analytic on the disk, then we can do our favorite thing in the whole course, which is to take the power series expansion. So we know that close to W0, we can write G of W is equal to, just an abstract power series expansion, which would then be of this form, and so on. We have this expansion, and this question I asked about how can we determine the inverse, well, the refined version of this question would be that the goal of today, then, or of this part of what I talk about today, is that we want to find the coefficients in the power series expansion. So we want to find the value of the AK, where k equals 0, 1, 2, and so on. And if we can do that, then we consider that we have found the inverse. Okay, so this still seems like quite a difficult problem, I would say. You just have some, you know that there exists an inverse if the f prime, if the derivative is non-zero. So it has a power series expansion, but how on earth could you possibly hope to use the information on your function f to determine the coefficients in the power series expansion of the function g? So to do this, we use some maybe non-obvious trick. So as so often, we want to consider a different but related function. And this function is w minus w0 times g prime of w. And why do we consider this function? Well, the reason is that if we do this, then h of w. So of course, g of w, I had it explicitly as a power series expansion, and I can differentiate it term by term, and then I multiply by w minus w0. So the power series expansion of h will be strongly related to this. So what happens is that the constant term, a0, it vanished because I took the derivative. Then I will have a1 times w minus w0. Then I will have 2a2 times w minus w0 squared. And I will have 3a3 times w minus w0 cubed, and so on. So this will be equal to the sum from n equal 1 to infinity of an times w minus w0, bn, where bn is equal to n times an. Okay? So if I just work now with this h, and I write it as a power series expansion, and if I can determine the coefficients in the expansion of h, then I will get the coefficients also of the original function that I was interested in, namely the coefficients of g itself. Okay? Just by dividing by n, the coefficients that I find. Okay, so to determine this, we're now going to use Cauchy's formula. And we're going to use some argument principle things. So by Cauchy's formula, we know that these coefficients of h, well, they are given, so they can also be given by integration along any suitable closed path. You remember they are given by this formula. So where gamma is any closed path, okay, and I just need one condition on this gamma for this theorem to hold. And if you remember, this condition was that the winding number around W0 had to be equal to 1. Okay, so now I will want to choose this gamma in a nice way. So typically you would choose something like a circle or something. But now this is in the image plane. So this is around W0. Okay, so I have my Z0 here in the Z plane. And then I have W0 somewhere over here in the W plane. And then when then I want to choose some simple curve around W0, where I want to at least control the winding number of this curve. But I will also want to work with some integrals on this curve around Z0 for the proof later. So I want it to be simple also here. And then the claim that I have, or that we will show, is the following. So I will just take a small circle around of radius epsilon here, around Z0. So this one obviously has, so let's call it C. So then obviously the winding number around Z0 here is equal to 1. But then we look at the image under F. So F was the name of my mapping, right? And G was the inverse of this one. So if I look at the image under F, then it could be a priori something very complicated. I mean, it's just, F is just any holomorphic map whose derivative does not vanish in Z0. We had no other hypothesis. So I have to assume that it does something very complicated. So it could really do something maybe like this, okay? Just to show you, illustrate that it could have a very complicated behavior. But then the question is, so in this picture, so I claim that the winding number of this curve around W0, well, what would it be? Actually, the claim is that the winding number of this F composed with C around W0 will still actually be equal to 1.
By argument principle.
By the argument principle, exactly. That's absolutely correct. And the reason, so the claim, so let me just write it down formally. So let me write down here. So the claim is that, so if T of t is this curve epsilon times e to the it, where t goes from 0 to 2 pi, then if we look at the image curve, and we call it gamma, is this curve, then this satisfies that the winding number around W0 is equal to 1. And the proof is exactly as you said. It's by the argument principle. How can we see this? So the reason for this would then be that I will just write a few lines to give you an idea here of why this is true. But by the argument principle, this n, the winding number around this gamma, which was f composed with c, in W0. So the definition of winding number was that it equaled this integral around this image curve, so around the complicated curve now. So we have the complicated curve, but a simple integrand, dw divided by w minus w0. On the other hand, this one equals, so as we saw in the first course on integration, this one equals the integral on c. So just now we moved from this very complicated curve in the w plane to this very simple circle in the z plane. So we integrate over this minus w0 dz. Okay, and then by the argument principle, so this is where we use it. This integral here would then be the winding number, but of the function, if we call this the function g, call this, so this is, or not g, let's call it something else, j. If this is j of z, then this one is j prime of z, because this taking minus w doesn't change this fact. So then this is just equal to, by the argument principle, n, so it's the winding number over c of the AJs, where the sum is taken over all the AJ zeros now of f of z minus w0 inside this circle, inside this disk, defined by c. But we could take this, so this c had radius epsilon. So taking epsilon small enough, using the fact that zeros of holomorphic functions are always isolated, we can assume that there is only one. So this is taking this epsilon, the radius of the disk, small enough. We can assume that there is only one term in this one. And the zero, I mean z0 is then the only zero. So this is the winding number of the disk around z0, and this is then equal to 1, as we have seen. Okay, so if we then recap, what we showed with this two-line computation was that the winding number of this very complicated curve around w0, which is equal to f of z0, was equal to the winding number of just the simplest possible path, the circle around z0, which was 1. So then we proved this claim. And then we just remember why we wanted to do this. Well, we wanted to do this to say that the Cauchy's formula actually applies, and we are allowed to compute the Bn using this formula. Okay, so what we get so Cauchy's formula indeed applies. Now we have checked that we are allowed to do that. So I write down again. So now we are going to use gamma, which is F composed with C. Okay. So that gamma prime of T is equal to F prime of C of T times C prime of T. So using all these things, we get that these coefficients Bn are given by H of W. So now we just have this string of computations here. N plus 1 dW, which by the definition of how we are allowed to integrate these things, we get that this is H of gamma of T divided by gamma of T minus W0 to the N plus 1. And then I have to multiply here by gamma prime of T, if you remember this definition here. And now I claim that this is equal. So it's not difficult, this. It's just a matter of checking these computations. So the question is only if I'm skipping too fast, but I think it's okay. So it's equal to this. So there are slightly more details in the notes, by the way. So I will scan them as usual and give them to you. And then you can see that it's equal to this. Okay, so F prime composed with C of T, this is just, so this is just part of the gamma prime of T here. And then, okay, so it's equal to this, I claim. So you can check this, it's not difficult. And now these two cancel out. Okay. And so do these. So I mean, these are the same thing, but we have to the power n plus 1 over here. So this is equal to 1 over 2 pi I, the integral from 0 to 2 pi of just T divided by F of C of T minus W0 to the n, which another way of writing this would be to integrate over C, the disk. Because, of course, from 0 to 2 pi, what I'm doing is actually I'm going around the disk. So of F of Z minus W0 to the n. And then I'm going to use this trick where I multiply and divide by the same thing. So what I'm going to do is to write this as Z minus Z0 to the n divided by this. And then I have to multiply by dz divided by z minus z0 to the n. So I've just multiplied by 1. So doing this thing. But the point now is that I want to study in more detail this function, which is here. Okay, and the next step in order to proceed here is that I want to expand this in a power series. So and of course, when I expand this in a power series, so this is f of z0, and this will clearly just depend on the coefficients then of f in a certain way. So let's see how it depends on the coefficients of f, that we can do this. So to expand this into a power series, we note that f of z, so f is holomorphic, so it has some power series expansion. And this taking minus a constant doesn't change the fact that it's holomorphic. So we can find an abstract power series expansion of this f of z minus w0. So this one, let's write it using some coefficients. So it's d1 times z minus z0 and so on, where d1 is the first non-zero coefficient. Of course, the constant coefficient here is equal to 0 because f of z was equal to, w0 is f of z0. So there is no d0 in this expansion. So we just look at this. And this one converges in some disk centered in z0 of some radius r. So this is just abstract to say that every power series expansion has some radius of convergence. And now we look then at, so let me write it, j of z would be this function f of z0 minus w0 over z minus z0. Well, then what is this? It's equal to the same thing, just I divide by this. So it's equal to d1 plus d2 times z minus z0 plus and so on. And this one still converges in the same disk. And then you remembered that you can also divide actually by power series, and it's still going to be a power series. So we talked about this some, 5 lectures ago, maybe, something like that. So I can have some other coefficients. Now C0 plus C1 plus C2 and so on. It's now the power series expansion of 1 over j. And why am I looking at 1 over j? Well, it's because what I'm interested in is 1 over j to the power n. It's exactly the one which appears in the integrand where I stopped in my calculation earlier. Okay, and this one has positive radius of convergence as well, just to make sure that all of these things actually converge and make sense locally. And this means that if I look at 1 over j of z, okay, so this one has some power series expansion. And more generally, I can look at 1 over j to the power k. And then I will say that this one has coefficients that I denote like this, C0, and then with an index k within parentheses, like this. That's C2 of k, z minus z0, okay, and so on. And then these coefficients, we see j of k, or whatever. We call this index ci of k. So these will be precisely the coefficients that I will be interested in, and these will be the ones that will determine actually the power series expansion of the inverse function. Right. So if you can find the power series expansion of this function 1 over j, defined as on this blackboard, to a suitable power, then you will actually be able to find the power series expansion of the inverse locally around this point. This is the claim. So now to go back to the computation, let's see how to do this. So we call this star, where we left off at the computation. Call this star. So we get that star now equals, so it was 1 over 2 pi I, the integral over the disk of 1 over j to the power n of dz over z minus z0 to the n. And then I replace this 1 over j to the power n. So I can write it like this if you want, of course. So I can replace this by its power series expansion. And this is the key trick, right? So I replace it by its power series expansion, and I get that this is equal to the sum like this. And then I get an integral over here. And the integral is exactly this one. Z minus Z0 to the power m minus n and then I put plus 1, because I do this where I put dz over z minus z0. So I put this here. So this plus 1 over here is related exactly to the fact that I also wanted to divide here, so I added a plus 1. And then I close the parenthesis. Now the question is, what does this integral equal? Okay, so what does this equal? So this could be a question for you. So we have different cases. So either the exponent here is equal to 0 or it's not equal to 0. So the first case is maybe if it's if this exponent is not equal to 0, then what would be the value of the integral?
Zero.
0.
Exactly. Very good. So then this would be 0 if m is not equal to, this is not 0, means that m is not equal to n minus 1. And if m is indeed equal to n minus 1, then what would be the value of this integral?
Winding number.
Exactly. So it's the winding number. So it's equal to this. So it's the winding number of the disk around z0, and this winding number is just equal to 1. So it's 0 except for one coefficient, which is when this is equal to 0, and then it's equal to 1. Okay, so that simplifies a lot our life, right? We have this. It means that we can disregard almost all the terms except the one where m is equal to n minus 1. So this means that this sum here is equal to the sum. Yeah, actually, it's not even equal to the sum. It's just equal to the only coefficient that survives in this sum is the one where m is equal to n minus 1. So it's equal to this coefficient. Okay, and so to remember, just to recap what we were actually computing, this was equal then to Bn, which was the coefficients in the power series expansion of H. Okay, so I'm running slightly out of space on that board, so I will continue here. Okay, so I think we stopped filming now, by the way, if you want to feel less on the spot. But feel free to keep your video on. I mean, I like it. It's nice. But okay, so we got Bn equal to Cn minus 1 equal to this coefficient, which is then equal to n times an, where you remember that an were the coefficients that we were looking for of the inverse. Okay, so in otherwise put, an is equal to 1 over n times Cn minus 1 of n, this coefficient. Okay, these were the coefficients for the inverse, for the local inverse G. Okay, so this technique is called Lagrange Conversion. Okay, so far nobody has been able to find this during the first homework, right? But now at the end of the course, I hope that you will be able to do this kind of thing. So finally, we can solve the homework problem. So let me just finish the part on Lagrange inversion by doing this. So then we had, just to see how you apply this, because you might not remember exactly what was Bn, what was An, what was Cn, and so on. So our function now is f of z is equal to z e to the minus z. Now we're interested in the point z0 equals 0. And we note in particular then that f prime of z0 is non-zero. So we can apply this. But more importantly, we have a power series expansion, f of z, which is equal to z minus z squared over 1 factorial plus z cubed over 2 factorial, and so on. And then what we wanted was to use this formula. So an was 1 over n times cn minus 1 over n. So what was this? So this index n in the parentheses means that we were looking at this 1 over j, if you remember, to the power n. And then we looked at the n minus first coefficient of this. So it means that we want to look at the following. So we wanted to look at z divided by f of z to the power n. So in general, we would take z minus z0 here, right? So we look at this, and then we find that this is actually just equal to e to the nz. And e to the nz, we need the power series expansion of this. And this is all we're going to need to find the local, the power series expansion of the local inverse of z to the e to the minus z. So the power series of this, okay, it's simple. It's just 1 plus nz over 1 factorial plus n squared over 2 factorial z squared, and so on. And by so on, so let me write down the n minus first coefficient, because this is the one I'll need. Actually the nth coefficient, sorry. So this is the one. Yes.
Isn't it z to the n minus 1?
Yeah, you're right, yeah. Is z to the n minus 1? Yes, thank you. And this is exactly what I need, which is what confused me there for 1 second. So remember, again, what I needed. So I wanted the n minus first coefficient. So this is precisely what I need. That means that this is Cn minus 1 with the index n. So the n was because I took z over f of z to the power n. And this is the n minus first coefficient. Okay, great. And then I just apply the formula up there. And I get that the inverse the local inverse g of z, or g of w, or whatever, of f of z at z equals 0 is given by the sum of an wn, okay, where an was equal to 1 over n times the cn. So it's actually equal to the following sum of n to the power n minus 1 divided by n times n minus 1 factorial, so n factorial, times w power n. And then we can, just as a bonus, so this then defines local inverse. So underline this. And we have also the radius of convergence that we can check. So we can check that. Then we have to look at the absolute value of the quotient of its coefficients, which is equal to the following. This can't be right. Okay. Anyway, this is supposed to be equal to this. And this, of course, goes to 1 over e. Okay. I think what I wrote in the notes was I made some arithmetic error. So claim, question, I hope this is correct, that the radius of convergence is 1 over e. So let's check this. Okay, I'm not gonna think about that now because I want to tell you about the last part as well. So this was what I wanted to tell you anyway about the Lagrange inversion. The point with a radius of convergence, it's not so important exactly what it is, but it has some positive radius of convergence. And it's kind of amazing, I think, that you can find the power series expansion of a local inverse with some method like this. Of course, it's not in any way obvious that the power series expansion of the inverse to z to the power e to the minus z around z equals 0 should look like this. So I think that's pretty remarkable. So I wanted to show you that anyway. Any questions about the Lagrange inversion? You're finished? Okay, thank you. Thank you. Okay, good luck for the rest. Bye. Okay, so next time you get this, this same question in a homework problem, you'll be able to impress the professor, right, with the answer, knowing how to deal with these Lagrange inversions.
Professor,
Yes.
is there integral formula, concrete integral formula for Lagrange inverse? I think in our last problem, in last homework 4,
Yeah.
I think it's integral formula for Lagrange inverse. The integral formula is 1 over 2 pi I integral z fz over fz minus fz 0. This is an inverse of f at point 0, z0.
Okay. Yes, I'm actually not sure. But I don't know really much about this, to be honest. So it's possible. I'd have to look into it if this is also true. But if you think about the argument that we just did, of course, these coefficients, Cn minus 1 and so on, they are expressed by integrals. So for sure, there has to be such a formula. But if it's exactly what you said or not, we have to, I mean, I don't know by heart. But,
Okay.
yeah. No, but it's a good point. So of course, yeah. So either in this case, you know the power series expansion, or, but you know, knowing a power series expansion, every coefficient is given by an integral. So in a sense, it's the same thing, right? And then the only question is, how can you express this integral?
Yes.
Yeah. Okay. So now the last part. Of course, I will talk about infinite products. I'll talk about gamma functions and zeta functions. Okay, so the gamma function and the zeta function. And this is a sort of brief remark on complex analysis applications in number theory, if you want. So, brief remark, complex analysis applications, number theory. Okay, and I warn you already now that, you know, my research, so I'm a complex geometer, I'm definitely not a number theorist. So in fact, I think one of your colleagues even wrote some, I don't know, maybe a bachelor's thesis or something on this topic. So she will probably know more than me even about some of this number theoretic stuff. But what I do know is complex analysis, and what we do know is complex analysis. So let's try to understand this problem, and in particular the Riemann hypothesis. Let's see what we can understand from our complex analysis point of view. So this is now the goal. So the first point is that many important functions in number theory. So why did I write infinite products here? Right? So many important functions in number theory can be represented actually by infinite products. And the most famous of these functions that can be represented in this way will be the Riemann zeta function. The Riemann zeta function, it will be written in the following way. So it will be equal to some infinite product of 1 minus Pn to the minus s, where Pn, so P1, P2, Pn, and so on, is an infinite sequence, ascending sequence of all of the prime numbers. So this is why the zeta function will have a connection to number theory. But this is going sort of too fast. It's getting ahead of myself. So I just wanted to show you why the word infinite product in the title. So we'll see this towards the end. But the actual definition, first, of a Riemann zeta function is the following. This is something that he introduced in 1859 in his paper. And by the way, I will use the original notation of this paper. And I even have it here. The paper is this one. I don't know if the camera will see. But it's this one, which is in German. I don't speak German. But über die Anzahl der Primzahlen unter einer gegebenen Größe. So it means on the number of primes below a given magnitude. And this was written in 1859. And it's not very long. And it still has such a big impact on the research of mathematics even today, which is kind of amazing. So this is something which is always nice to keep in mind, these historical perspectives. So the Riemann zeta function is given by the definition that he wrote down here on page 1 on this paper is the following, that it's the sum from n equals 1 to infinity of 1 divided, so you sum over 1 divided by n to the power s. Sorry, this is zeta of s. So this is my way of writing a zeta. I know it's not very, very good, but it's my handwriting. And s here is any complex number. So this is, of course, important. So you shouldn't think that this is a real number. So n here, it goes over the integers, but s is a complex number.
But
so this,
Professor, maybe divergent. If S is any complex number, then this series may be not convergent series.
Absolutely. You're absolutely correct. So this is what I will say next. So this one converges. So we have to ask about convergence of this. And it converges. So, okay, since you asked a question, maybe you also know when it converges.
Real part of n is greater than 1.
Real part of s, exactly.
Yes, yes.
Is greater than 1. So converges if the real part of s is greater than 1. So, and the notation that Riemann used for this was he wrote the real part as sigma and the imaginary part as t. Okay. Okay, and we define this sum, and we consider it whenever sigma is greater than 1, because it converges exactly when this happens, exactly as you said. So why does it converge if sigma is greater than 1? So this is the question.
Harmonic series, just.
Exactly. So you compare with this series, and you can use the M test if you want. So you note that 1 over absolute value of n to the s is equal to 1 over n to the sigma. And you know that this series now n sigma converges if sigma is now a real number, because it's the real part of the complex number s. So you know that this converges if sigma is larger than 1. And then if you remember the M test, so by the M test, something we did in lecture 3, I believe, so implies that this sum of 1 over n to the s, this way you define it, so this converges so absolutely and uniformly on any set, I mean, for sigma greater than or equal to some fixed sigma 0 greater than 1. And what does this imply? Well, this implies that this psi of s equal to this sum now defines actually an analytic function defines an analytic function on this set of all the complex numbers with real part greater than or equal to 1. Okay, so if this is 1, we know that this function that we wrote down, it is well defined and it's analytic here on this domain, where the real part is greater than 1. And then the goal, the question, can we extend it to all of the complex plane? And the answer is almost yes. So it will be possible to extend it to a meromorphic function, but which has only one pole. And then it's analytic away from this single pole, which is in s equals 0. And then it has a bunch of zeros, this meromorphic function. And this is exactly what the Riemann hypothesis will be about. But to discuss this, we first have to introduce the second player. So, so the topic is extension of psi of s to all of C. And to do this, we need to consider also the gamma function. So we make a little intermezzo, a little pause here in our study of the zeta function to consider the gamma function, which was introduced by Euler. Okay, so I am proud to say, by the way, that Euler was the advisor of my advisor of my advisor of my advisor of my advisor, and so on. So this is very nice. So it's literally my academic great-great-great-great-grandfather. So gamma of S was defined. This is by the case. This is by the way the case for many people, that either Euler or Gauss was the advisor of their advisor of the advisor, and so on. At least in Europe, this is often the case. So x to the power s e to the minus x times dx over x. So I write it a bit bizarrely like this, dx over x. Okay, this is some convention. I could, of course, just as well have put s minus 1 here. So this is just now x is some real number. You integrate over this variable, but s is still our complex number. Okay, so this is the gamma function. And the claim, okay, so this is Euler's gamma function. Leonhard Euler, who went blind in later years, but kept doing mathematics anyway. The claim gamma of S is analytic. So now we're going to do a similar thing to how we started out for the zeta function, find a region where it is analytic. So the claim is that it's analytic on the real part greater than, not greater than 1, but greater than 0. Okay, it's a different function. So this one is analytic on this domain. Okay, and the proof of this is sort of elementary. So this is something you can do. So I'm writing this because, of course, in this story, it's going to lead up to the most difficult unsolved problem in mathematics. So I feel I should definitely point out to you what is possible to do and for you to go and read in a book and understand, and what is actually the really difficult part. So this proof is elementary, can be found in a book, can be found in books. For example, Alfors. Okay, I will not put it on the board right now, but you can definitely go and read this, and you will be able to understand it. Okay, so then the second thing is that, so what I want to tell you about this gamma function is that it's actually heavily used in number theory for one simple reason, and the reason is the following. But if you take integration by parts, okay, so integration by parts, where we take u is equal to x to the s, so du is equal to s x to the s minus 1 dx, and then we take dv to be equal to e to the minus x dx, which means that v is equal to minus e to the minus x. So using this, I don't know how you write integration by parts. This is how I usually write it. So then we get that gamma of s plus 1. So if I look at this, then it's equal to the integral from 0 to infinity of e to the minus x to the s dx. I mean, this was the definition of gamma of s plus 1. And now using the integration by parts with this here, we get minus e to the minus x to the s, evaluated in 0 and infinity, plus s times the following integral. The integration is over x, as usual. And this thing here is equal to gamma of s. So this was gamma of s plus 1. And this thing here is equal to gamma of s. Okay, and this thing here will be equal to 0. So what this gives is the following famous relation. So if you want to remember something about the gamma function, so there are very many properties that it has, but this is definitely, I would say, the main one. So gamma of s plus 1 is equal to s times gamma of s. And again, I should say that for now, we are on this set where it is analytic and everything is nice. So when the real part of s is greater than 0. So what does this mean? I mean, so moreover, we also have that we can compute gamma of 1. So gamma of 1 is just equal to this integral from 0 to infinity of e to the minus x dx. And then you do some calculus from the first year to see that this is equal to 1. So gamma of 1 equals 1, and gamma of s plus 1 equals s times gamma of s. So this means that gamma of 2, is equal to, gamma of 2 is equal to gamma of 1 and so on. But let me say here that gamma of n plus 1, let me write it like this, is equal to n, gamma of n, which is equal to n times n minus 1, gamma of n minus 1, and so on, which will give, in the end, that the last one, because gamma of 1 is equal to 1, we will get that it's equal to n times n minus 1 times n minus 2, and so on, and it will end on 1. And this, what is this? Well, of course, everybody recognizes n factorial here. So what it means is that gamma of n plus 1 is equal to n factorial. So in other words, this gamma function, one of the reasons why it's so famous and used by number theorists, is that gamma analytically extends the factorial, this n factorial function, to this real part of s greater than 0. Okay, so this is one very nice thing about the gamma function. But it is not all that we will need in order to do what we want to do for the zeta function, because ultimately that's what we are most interested in. The reason why we are talking about this gamma function is that there is a very nice relation between the gamma and the zeta functions, which will be useful to us. Okay, and what is this relation? So okay, so by the way, we can also extend, so let me write down this fact, and then I can say something about the explanation before I tell you about the relation between gamma and zeta. I wanted to also say this, that, so by induction, I will explain what I mean by that. Gamma of S, we can actually extend it to a meromorphic function. So extends to a meromorphic function on all of C, which has certain poles. So with poles at S equal to -1, no, really not true. So 0, I mean, it's true, but not all of it. So at 0, -1, -2, -3, and so on. And we can also compute the residues. So the residue of this, so now I write gamma of S for the meromorphic extension. So this meromorphic extension at the point -n, where n is a positive number, positive integer, is -1 to the n divided by n factorial, where n, well, yeah, it's 0, 1, 2, and so on. Okay, and why is this? So let me just say quickly, what is the reason for this? It's because from this relation, gamma of S plus 1 is equal to gamma of S. We can define gamma of S. So what should it be? Well, it should be gamma of S plus 1 divided by S. So, of course, we know that this gamma function was a priori defined so far when the real part of S was greater than 0. But now, if I look at the right-hand side here, this one is defined when S plus 1 is greater than 0 in the real part. So the real part of S plus 1 is greater than 0, which means that the real part of S is greater than -1. So I have gained some ground, right? So I can now extend it. If this works, I could extend it so it's defined when real part of S is greater than -1 instead of greater than 0. And then I could repeat this thing. Once it's defined in -1, I could repeat it and say that, aha, but then I can define it in real part of S greater than -2, and so on. And then I will go on to define it on the whole plane. Okay, so this function here, so what do we know about it? We know that this one is analytic, gamma of S plus 1, using this condition. But then we divide by S. So it will actually be a meromorphic function with a simple pole at S equals 0. It's simple pole because the analyticity of this means that it doesn't interfere with the order of the poles. Okay, so this one is meromorphic with a simple pole at S equals 0, and we can also compute its residue, which is given by the limit as S goes to 0 of S times this gamma of S plus 1 over S. Of course, these cancel, and this is equal to gamma of just 0 plus 1, so gamma of 1 And this was the integral from calculus, from first year calculus, which was equal to 1. So we know that the residue here is equal to 1. And then we can repeat process by setting then that gamma of S will then be gamma of S plus 2 divided by S times S plus 1, defined for real part of S greater than minus 2, and so on and so forth. And doing this, we can eventually reach this fact here that by induction, gamma of S extends to a meromorphic function on the whole complex plane with poles at S equals 0, so simple poles at S equals 0, minus 1, minus 2, with residue equal to this. So actually, with poles here, with residue equal to this, is what I should say, not simple. Okay, so this was the gamma function, extends to a meromorphic function on the whole plane. And the next step is to see the relationship between the gamma and the zeta function. The relationship between gamma of S and zeta of S. So how can we relate them? So they look like they have maybe nothing particular to do with each other, but actually they do. So for the moment, consider first the real part of S greater than 1, which is where our zeta function is for the moment defined, even though we will extend it. So the idea here is that replacing x by n times x in the definition of a gamma function, okay, which again, I will write it. Okay, now I wrote it like this, without dividing by x here. So this gives the following. It gives that 1 over n to the s times gamma of s is equal to 0 to infinity. Okay, and so this is good. So what I'm claiming is that if you replace x by nx in this thing, then you have this 1 over n to the s factor that comes out, and you can put it on this side. So 1 divided by n to the s times gamma of s is equal to some integral. Now this is good, right, because the definition at the moment of the zeta function was the sum over all positive integers of this 1 over n to the s. So what I can do is summing up. So summing up on both sides, I will actually get, on the left-hand side, I will get the zeta function of s times the gamma function of s. And on the right-hand side, well, I will get the sum here, where n equals 1 to infinity of these integrals, okay? And I'm not very careful in this talk about many details, including why I can, sometimes maybe interchange sums and integrals and so on. So, and yeah, the first point where I will just sweep this under the rug a little bit, or not emphasize this too much, is here. So we want to rewrite this in some way. So we note that this integral here, so it's equal to this. So if I change the sum and the integration, I can put the sum inside here, summing over e to the minus nx, and then dx. And then I can use the geometric series to see what this sum of e to the minus nx is. So there are some simple computations here to be made, but the claim is that this is equal to 0, the integral from 0 to infinity of x to the s minus 1 divided by e to the x minus 1 dx, okay, and so on. And then, comes details that I cannot possibly have a time to do here. So along these lines, I wanted to illustrate this because this is really the key. This explains already why you can relate gamma and zeta, and they are related by the fact that their product is equal to some simple integral from 0 to infinity in a real number, but where s is a complex number. And along these lines, we actually get the following theorem then, which I will just state without rigorous proof, because of course this is a course in itself to go through all this. So now it's a small panorama. So gamma of s will then be equal to the following. So this you can read about in Alfors, by the way. So I don't give a proof, but the proof is in Alfors. And it's not impossible at all to understand. So we have this formula. And let me just say in words, so where this minus z to the s minus 1, this is defined, or well, okay, maybe I should write it. So where minus z to the s minus 1 is defined using the branch on C minus 0 to infinity. So we remove the positive real axis in order to define this, this power function. So I don't say more than that. And C is the infinite path given in the following picture. So it's the infinite path that goes essentially around a circle, but then it goes out along the axes, and it goes in this direction. You have some infinite path, and you have this integral. Okay, so this integral, I don't want, or I don't have time to go into too much what are the properties of this integral, or why you choose such a contour, and so on. So for this, you just have to read in Alfors. So this is Alfors. I think I even wrote down which page somewhere, but maybe I didn't. Okay, so see Alfors. Okay, for this. So now assume that this theorem holds. Then we also have the following claims. Actually, maybe I want to write in some other color. So we have the following claims. Which are that, first of all, this integral part here, you can check that this is entire. So it's holomorphic on the entire complex plane, which is good because it means it doesn't interfere with any poles. It doesn't add any poles to this. And then you can look at gamma of 1 minus s. So where are the poles of gamma of 1 minus s? Well, we should remember that we found the poles of the gamma function. It was when the argument, in this case 1 minus s, was equal to 0, minus 1, minus 2, minus 3, and so on. So 1 minus s equals to 0, minus 1, minus 2, minus 3, and so on, means that s is equal to 1, 2, and so on. So 1 minus s equal to 0, minus 1, minus 2. So these are the poles of this gamma function. So this one is entire, and this one has poles when s is equal to 1, 2, and so on. Which then means that it says something about the gamma function here. But of course, the zeros can be cancelled out. So the conclusion that you can see immediately from this equation would be the following. Okay, so the conclusion is that this zeta function is analytic. I mean, using that zeta is analytic for real part of S greater than 1 implies that it has poles implies that its poles, which it has, so at n equals, I mean the poles of gamma of, yeah, so this is what I want to say, sorry. So poles of gamma of 1 minus s at s equals 2, 3, and so on, must cancel against zeros of the integral part. So of this integral over this curve C, which I said was entire. I just made this claim, right? It's possible to prove. Okay, and finally, so what I'm doing now is just some very quick, because there's not much time, analysis of the zeros and the poles, thanks to this kind of relations, and thanks to the fact that we know stuff about the gamma function and its poles. So at s equals 1, this gamma of 1 minus s has a simple pole with residue 1. Okay, so we recall this. And this, along such line, we have a following claim or theorem that this zeta function of s can be, so also the zeta function, just like we did with the gamma function, can be extended to a meromorphic function on all of C, whose only poles, well, there's only one pole, is a simple pole at s equals 0. Sorry, s equals 1, actually. Sorry, this is the pole with the real part, with residue at 1 is equal to 1. Okay, so this is the claim. So you can prove this. The point is now you can extend the zeta function, just like we did with the gamma function, to a meromorphic function on the whole complex plane. So what about zeros of gamma of s? So this is what the Riemann hypothesis is about. So then we have a so-called functional equation, which is given by the following. And I'm sorry if I am hurrying now because the time is up and we do want to have lunch. Sine of pi s over s, gamma of 1 minus s. Sorry, I'll have to write this over here. I need some more space. Just forget that. Okay, so the functional equation says that gamma of s is equal to 2 to the power s, pi to the s minus 1, sine of pi s divided by 2, times gamma of 1 minus s psi of, no, zeta, sorry, of 1 minus s. So I don't know if I said psi before, but zeta and zeta. So zeta of 1 minus s. So you have this. And this is where it becomes really interesting. This is because, so this implies that this zeta of s has the so-called trivial zeros. which is when sine of pi s divided by 2 is 0. But not only I want sine of pi s divided by 2 to be 0, but I have a second condition. And the second condition is that this gamma might have poles. So this should have no poles. Has no poles. So this will mean, if you put this together, that the trivial zeros, so you just have to put together carefully. You can read in the notes. It's more explicitly written. That you get trivial zeros at s equals -2, -4, -6, and so on. So the even negative integers. OK, so you get, in other words, this meromorphic extension of the zeta function, which has a pole in s equals 1, and then it has these trivial zeros in -2, -4, -6, and so on. And then we want to discuss, or what I wanted to discuss is its connection now with why we really care about this function, which is the connection with number theory. See if I can finish this in the next 5 minutes, 10 minutes, 7 minutes. So connection with number theory is the following. And this was the focus in Riemann's original paper that I showed you. It's important in number theory because of the following. That for the real part of s greater than 1, which is typically what you're interested in anyway, in number theory, we have that 1 divided by zeta to the s is equal to this product, this infinite product, of 1 minus 1 over Pn to the s, where P1, P2, Pn, and so on is an ascending sequence of primes. So of all primes, right? So you take all the primes and you list them in an increasing order, and then you have this formula that 1 over the zeta function is equal to this, which is exactly the root to the fact that if you learn about the zeros of the zeta function, then this will say a lot about the distribution of primes, okay, which is a huge topic of research, right? So the sketch of a proof of this. So first of all, I should tell you that the following fact. What does it mean for this, this thing to converge here? So recall that the product of some sequence like this is said to converge. So with 1 plus an all non-zero converges if and only if the sum, so by definition you ask that the sum of log of 1 plus an converges. And this is a sort of theorem or a proposition that this happens if and only if the sum of the absolute value of an converges. Okay, so this is what it means very quickly for such a thing to converge. And now for the proof, let sigma be the real part of S and assume that it's greater than 1. How can we now show that this zeta function must be equal to this product development? So then, first of all, we see that that it converges. Okay, so you can read about that in the notes. So converges. So this product of 1 minus 1 over Pn to the S converges. This is by the M test. The details are in the notes. It's just a few lines. And then assuming that sigma is greater than 1, we now do the following observation here, which is at the heart of everything. So the zeta function of s times 1 minus 2 to the power minus s. So this is equal to the sum of n equals 1 to infinity, where I sum over n to minus s. But then I have a power 2 that's also, so the definition of this is the sum of 1 over n to the power s. And then I multiply by this, so I get times 1, I get this, exactly the zeta function, minus the sum over n equals 1 to infinity of 2n to the power minus s. And this, another way of writing this is just that it's the sum over all numbers n, m, which are not divisible by 2. Okay? So by doing this, multiplying by 1 minus 2 to the power minus s, I remove from this sum, where if I took all of the integers, it would be the zeta function, but now I removed all the ones divisible by 2. Now in the same way, if I multiply, I take also the next prime, then this will be sum over m to the minus s, where m is not divisible by 2 and not by 3, and so on. And actually, this thing times the product from 1 to n of 1 minus 1 over Pn to the s will be the sum of m to minus s, where 2 does not divide m, and all the way down to to Pn, so the nth prime does not divide m either. Okay, so this sum starts with 1, and then the next one is P n plus 1. So it starts with 1, and then it is some remainder term. And what we'll get is that the limit, so you can check this claim, that as n goes to plus infinity, and you do something like this, we check that the zeta function of s times the product, so this thing I wrote over here, okay, this is equal to 1. And this will imply that 1 over zeta of s is actually equal to the limit of this thing, which is what we wanted to prove. Okay. That was very quick, but that's how it is, because despite starting early, I am late. Okay, and now let us write down, finally, just finish the course by writing down the Riemann hypothesis. So first, let me just say in words, so the discussion. So let me summarize what we have so far. So we have so far, but by the product development, by what we just did, we can see, so if you go back and think about this, this very rushed presentation, you can see that this zeta function has no zeros in the plane, in the part of the plane. So this is 1. So if the real part of s is greater than 1, there are no zeros, okay? So no zeros of zeta. In this region. This is the first thing. And the reason for this is that if it had zeros, then by the product development here, then this one would not be finite, but we know that it converges. Actually, this is a finite number, so it could not have a zero of the zeta of s when the real part of s is greater than 1, which is when this is finite. So there are no zeros in here. You can also see by the functional equation, so no zeros of zeta of s here, by the functional equation. So what this does is that it leaves us with this little strip here. And it says that all zeros no zeros here, sorry, except the trivial ones. The trivial zeros were those when the sign of pi times s over 2 had zeros, but which were not cancelled out by poles. So it was in this minus 2, it was in minus 4, and so on, minus 6. So we had these zeros here, and these are the only one. So all other zeros are in the critical strip the real part of S between 0 and 1. So they are in here. All the zeros that are not the trivial ones that you could find easily. And actually then the Riemann hypothesis says that not only all the zeros are in there, but it conjectures that all the zeros are on this line, real part of S is equal to 1/2. Okay, so the Riemann hypothesis, to write it down, and then I'll stop. It says that all non-trivial zeros of the meromorphic function, so we extended this zeta to a meromorphic function on C, are on what is called the critical line defined by the real part of S is equal to 1/2. And this is, as you know, so it's a Hilbert's 8th problem. It's a Millennium Prize problem, and they are very famous because this has huge implications in number theory for the understanding of primes, precisely because this product development. And let me just finish by saying that it is perhaps then, as you know, the most famous unsolved problem in mathematics. So one of the most famous unsolved problems in mathematics. Okay, so sorry about that. It was a bit quick. It's 12:45. I will stop here. So if you have any questions, if they are quick now, otherwise, we'll Skype again or something, or you can always email me and I can answer questions. There are other famous problems in mathematics too. So for example, the Millennium Problems, so they are the Young-Mills, I wrote them down, so it's the Young-Mills and mass gap, Riemann hypothesis, the P versus NP, Navier-Stokes, the Hodge conjecture, the Poincaré conjecture, which was solved, and the Brick and Swinnerton-Dyer conjecture, which is about elliptic curves. And there are tons of other famous problems all over mathematics, not only in number theory, of course. But anyway, I hope this gives you some kind of flavor of what you can look into to be able to, fill in the details of this story about the Riemann hypothesis. At least understand that you can write down some series or some infinite product, and then you can extend this to a meromorphic function on the whole plane, and then you can ask about poles, you can ask about zeros. We also solve a gamma function, and all these relations between these functions. There are many more. And then, for some reason, this innocent-looking statement here with the Riemann hypothesis has turned out to be very difficult, and it has been a long-standing open problem for a long time. So, okay, thank you. Any questions?
Excuse me, can you hear me?
Sorry, I don't hear you very well, Junaid.
I think
Try again, maybe I'll hear.
Now?
Yeah, it's okay, it's okay.
Yeah, okay, thank you. Last year, I think Sir Michael Atiyah claimed that he have proved this thing, but then there was some gaps.
Yeah.
Yeah, and are the scientists still working on the Michael Atiyah's approach, or it is totally wrong?
I think it is totally wrong, as far as I know.
Oh, okay.
Yeah, it's totally wrong. And it's by far not the first one to be totally wrong. I mean, I think every year there are probably, you know, a dozen of people that are totally wrong about the Riemann hypothesis. I mean, some are more obviously wrong than others, of course. I'm not saying that Michael Atiyah was obviously wrong, but it was wrong. It had a gap. And I mean, also amateurs, right? You know, someone sitting in their living room watching a video about the Riemann hypothesis, and then they say, ah, look, I proved it. It's 5 pages and it works, but then it doesn't work. And of course, somebody like that could prove it. You know, it's not impossible at all. So all of you watching, you know, you can try, but it's very hard. Nobody could do it in all these 150 years, you know, it's been open. So yeah, including this approach by Michael Atiyah. It was wrong. But even the incorrect proofs often give us some new mathematical ideas and insights, so it can be valuable in itself. Okay, any other questions? Okay, so then I would just like to thank you again for the course, I mean, for attending. And we have one last homework left, and then the exam. And I mean, I'm here in my office or on email or on Zoom, so for any questions. And of course, also Alejandra is there with the tutorials. So thank you. And when is the last homework? So I decided you could have until December 2nd when there is a tutorial, because so I know this happens to be the day maybe before your real analysis exam, but of course you are allowed to do it now if you want. So it's just a question about giving you some more flexibility to plan your time on it. So up until December 2nd, you can hand it in. Okay, and on the last homework, there are many more exercises that, I mean, just as some training for the exam. Okay, thank you for that comment, Junaid and Ling, and all the rest of you. And yeah, it's been very nice to teach this course, even though it's sad that I haven't been able to see more of you. I mean, some of you I haven't met even once, so it would be really nice to do that. I hope I'll be able to do so during the rest of the year, at the very least. And yeah, and good luck. Now let's go have lunch before we close. Okay, so thank you.